G'day, science lovers. Have you ever looked up at the night sky, at that vast, inky blackness peppered with countless stars, and wondered if the same rules apply out there as they do down here? We live our lives on this tiny blue marble, utterly confident that if we drop an apple, it will fall to the ground. We trust that the sun will rise tomorrow, bringing light and warmth to our world. This certainty is built on a profound assumption, one that underpins all of modern science. It is the belief that the laws of physics are universal, that they are the same yesterday, today, and forever, not just on Earth, but in the most distant galaxies imaginable. It's a comforting thought, isn't it? A bit of cosmic order in what can often feel like a chaotic existence. This idea of universal laws is the bedrock upon which we have built our entire understanding of the cosmos. From the smallest subatomic particles whizzing around inside an atom to the colossal dance of galaxies across billions of light years, we assume a single, consistent rulebook. These rules are described by mathematics, and they contain some very special numbers known as the fundamental constants of nature. Think of them as the universe's own unique settings, the knobs and dials that were set at the very beginning of time. These constants dictate the strength of gravity, the speed of light, and the intricate interactions that govern everything from chemistry to the life cycle of stars. When you think of a universal constant, the first one that probably pops into your head is the speed of light. In physics, we call it Ca. It's a number so famous it features in the most iconic equation of all time, E equals mc squared. That Ce represents the ultimate speed limit of the universe. The constancy of the speed of light is a cornerstone of Albert Einstein's theories of relativity. He didn't just pluck this idea out of thin air. It was a radical but necessary conclusion to solve a major puzzle in 19th century physics. This isn't science fiction, it's a measurable reality that we have to account for every single day in technologies like the GPS satellites that orbit our planet. If we didn't adjust for these relativistic effects, your GPS would be inaccurate by several kilometers every day. Now let's journey from the vast scales of the cosmos, governed by Ce, down into the weird and wonderful world of the very small. Down here in the realm of atoms and particles, another constant reigns supreme. This one is called Planck's constant, represented by the letter H. Planck's constant essentially defines the graininess of reality at the smallest scales. It tells us that energy, like light, doesn't come in a smooth, continuous flow. Instead, it comes in tiny, discrete packets, or quanta. This was a revolutionary idea, first proposed by Max Planck in 1900 to solve a problem related to heat and light. It was the birth of quantum mechanics, a theory that would completely revolutionize our understanding of matter and energy and pave the way for technologies like lasers, computers, and nuclear power. Finally, let's zoom back out and consider the force that shapes the universe on the largest of scales, gravity. The fundamental constant associated with this force is known as the gravitational constant, or Big G. Big G dictates how strongly matter clumps together. It's the reason stars ignite, planets form, and galaxies hold together in their majestic spiral and elliptical shapes. Our existence depends on G having the value that it does, a value that is, as they say, just right. Of all the fundamental constants, Big G is notoriously the most difficult to measure with high precision. This is because gravity is an astonishingly weak force compared to others like electromagnetism. Measuring the feeble gravitational pull between two objects in a laboratory, while shielding them from all other vibrations and electrical interference, is an immense technical challenge. So we've met the main players, the cosmic speed limit C, the quantum architect H, and the universal pull G. We've also touched on alpha, the fine structure constant. The big question is, how do we know what their values are? And more importantly, how do we know if they're changing? The answer lies in one of the most painstaking and heroic endeavors in all of science, the art of measurement. This isn't just about getting a ruler out. It's a relentless, multi-generational quest for ever greater precision. This quest is driven by a simple but powerful idea. If we can measure a constant today in our lab, and then find a way to measure what its value was a billion years ago in a distant galaxy, we can compare the two. We have to use the universe itself as our laboratory, and the light traveling across it as our messenger. To hunt for changes in constants over time, we need a reliable clock. Not just any clock, but the most accurate timekeeping device ever created by humanity, the atomic clock. These clocks don't rely on a swinging pendulum or a vibrating quartz crystal. Instead, they use the quantum tick of an atom. An atomic clock works by using a laser to push an electron from one energy level to another. The frequency of the laser light has to be tuned perfectly to match the energy gap. This frequency is so stable and so precisely defined by the laws of quantum mechanics that it provides a near-perfect metronome. The best atomic clocks are so mind-bogglingly accurate that if you'd started one at the Big Bang 13.8 billion years ago, it would only be off by about half a second today. They are phenomenal feats of engineering. To look back in time, we need to become cosmic archaeologists. Our artifacts are not stone tools, but photons, particles of light that have traveled for billions of years across the universe. Our main tool is spectroscopy, the science of breaking light down into its constituent colors, like a prism creating a rainbow. When we do this with light from a distant star or quasar, we don't see a smooth, continuous rainbow. Instead, we see a spectrum that is crossed by dark lines. These are called absorption lines. They are created when light from the quasar passes through clouds of cold gas floating in intergalactic space on its long journey to Earth. Each chemical element in those gas clouds, like hydrogen, iron, or magnesium, absorbs light at a very specific set of frequencies, or colors. This creates a unique pattern of dark lines, a kind of cosmic barcode that tells us exactly what the cloud is made of. Crucially, the precise position of these barcode lines depends on the value of the fundamental constants, especially the fine structure constant, alpha. If alpha was different in that distant cloud, billions of years ago, the spacing between the lines in the barcode would be slightly different from the spacing we measure for the same elements in our labs today. This is the technique that was used by the Australian astronomers we mentioned earlier. They used the giant Keck telescopes in Hawaii to capture the faint light from ancient quasars. They then used incredibly precise spectrographs to analyze the barcodes from gas clouds that the light passed through when the universe was only half its current age. By painstakingly measuring the patterns of absorption lines from multiple different elements, they could search for a tiny shift compared to laboratory values. It was this analysis that led to the bombshell claim that the fine structure constant seemed to be slightly smaller in the distant past. The story got even stranger. The original team, led by Professor John Webb, didn't stop with their initial findings. They expanded their search, using more telescopes, like the European Southern Observatory's Very Large Telescope in Chile, to look at quasars in different parts of the sky. What they found was both tantalizing and deeply weird. The data seemed to suggest that the universe might be a bit lopsided. Their results pointed towards what they called a dipole. This means that if you look in one direction in the sky, towards a particular constellation, alpha in the distant past seems to be slightly smaller than it is today. But if you look in the complete opposite direction, 180 degrees across the sky, alpha seems to be slightly larger. This idea of a preferred direction in the universe is a direct challenge to the cosmological principle, the idea that the universe is basically the same in all directions. Our cosmic detective story has so far involved peering back in time by looking at light from distant quasars and running ultra-precise experiments in modern labs. But there's another, quite extraordinary way to test the constants in the past, and it doesn't require a telescope at all. We just have to dig. Deep beneath the surface of the Earth, in a uranium mine in Gabon, West Africa, scientists in the 1970s made a discovery that still boggles the mind. They found the remains of a natural nuclear reactor. That's right, a nuclear fission reactor that operated all by itself, without any human intervention, nearly 2 billion years ago. This incredible geological anomaly provides us with a unique laboratory for testing the laws of physics. When the reactor was running, it produced a whole suite of different elements as byproducts of the nuclear fission, just like a man-made reactor does. The relative amounts of these leftover isotopes depend very sensitively on the physics of the atomic nucleus. The Oklo reactor gives us a fantastic data point from 2 billion years ago, but what about other times and places? Astronomers have found another clever way to hunt for changing constants, this time by studying the corpses of stars. When a star like our Sun runs out of fuel, it sheds its outer layers, and its hot, dense core remains. This remnant is called a white dwarf. The atmosphere of a white dwarf is a very extreme environment. It has incredibly strong gravity, much stronger than on the surface of the Sun, This intense gravity has a powerful effect on the atoms in the white dwarf's thin atmosphere. It warps the structure of the atoms themselves, subtly shifting the energy levels of their electrons. When we look at the light from a white dwarf, we can see the absorption lines, the cosmic barcodes, from elements like iron and nickel in its atmosphere. The exact position of these lines is affected by this immense gravitational field, and the size of this shift depends once again on the value of the fine structure constant alpha. So we have a scientific puzzle on our hands. The lab experiments and some astronomical observations say the constants are rock solid, but other astronomical observations hint that they might be changing. Why is this consistency so important to us? Why don't we just accept that the universe is a bit messy? It's because the assumption of constancy isn't just a matter of convenience. It's the logical foundation upon which the entire scientific method is built when we look out into the cosmos. This principle is sometimes called the Copernican principle or the principle of mediocrity. It's the humble idea that we don't occupy a special privileged place in the universe. Think about how an astronomer works out the temperature of a distant star. They do it by analyzing its light spectrum. The patterns in that spectrum are governed by the laws of atomic physics, laws that depend on constants like alpha and h. The astronomer assumes that those laws and those constants are the same for that star as they are here on Earth. The mystery of the changing constants might not just be about the known constants themselves. It could be a signpost pointing towards something completely new, undiscovered fields or forces of nature. Many modern theories that try to unify gravity with quantum mechanics, like string theory, actually predict that our universe should be filled with very light invisible fields. This idea is incredibly exciting because it connects the search for varying constants to another huge mystery in cosmology: dark energy. We know that the expansion of the universe is accelerating, pushed apart by a mysterious repulsive force we've labeled dark energy. If these scalar fields exist, they should not only affect constants but also behave like a new, extremely weak force of nature. Experiments are now being designed to look for the tiny effects of such fields, hunting for these new forces, and indirectly for the cause of varying constants. Right, we've journeyed through the mind-bending experiments and the conflicting evidence. Now it's time to ask the big what if question. What if the wild claims are true? What if the skeptics are wrong and one or even all of the fundamental constants are actually changing? The consequences would be nothing short of reality-altering. A tiny change in a single number could set off a cascade of cosmic dominoes, toppling everything we thought we knew about the cosmos. The most immediate casualty would be the law of conservation of energy. This is one of the most sacred principles in all of physics. In a universe where, for example, the fine structure constant is slowly increasing, energy could be spontaneously created out of the vacuum of space. The universe would be getting a constant, free top-up of energy. This sounds great, but it would fundamentally break the logical consistency that underpins all of our physical theories. Let's get more specific. How would a changing universe affect the things we see around us, like the stars that light up our night sky? The life of a star is a delicate balancing act. It's a constant battle between the inward crush of its own gravity and the outward push of the nuclear fusion reactions happening in its core. The strength of both of these forces is governed by the fundamental constants. If you start fiddling with these dials, the star's life can change dramatically. Imagine, for instance, that the fine structure constant, alpha, was slowly increasing over cosmic time. This would affect the electromagnetic repulsion between protons inside a star's core, and it's not just about the star's brightness. The very elements that make up our planet and our bodies were forged inside ancient stars. The creation of elements like carbon, oxygen, and iron depends on a series of finely tuned nuclear reactions. One of the most critical is the process that makes carbon. This brings us to the most profound consequence of all, the impact on life itself. The universe appears to be exquisitely fine-tuned for our existence. As we've seen, if you change the value of constants like g or alpha by even a small amount, the universe becomes unrecognizable and hostile to life. But what if the constants are not fixed, but are instead evolving over time? This opens up a fascinating and entirely new perspective on the fine-tuning problem. Perhaps the constants don't have to be perfect from the very beginning. Maybe the universe itself is evolving and its physical laws are changing along with it. In this picture, there might have been vast epochs in the universe's past, or there might be huge regions of space where the constants have the wrong values and life is impossible. We just happen to find ourselves living in a particular cosmic era and a particular location where the dials have settled into the narrow, life-permitting range. So, after this epic journey across space and time, from the heart of an atom to the most distant quasars, where do we stand? We find ourselves at the edge of a great scientific cliffhanger. On one side, we have a mountain of evidence, built up over centuries, that supports the idea of a stable, predictable universe. On the other side of this chasm of uncertainty, we have the tantalizing, controversial evidence from those ancient quasars. This conflict between the different results is what makes this area of science so thrilling. It's a genuine frontline mystery where the experts don't agree. This isn't a sign that science is broken. It's a sign that science is working exactly as it should. The debate is fierce, the stakes are high, and every new experiment or observation adds another piece to this complex puzzle. We are forced to question our assumptions, refine our methods, and push our technology to the very brink of what is possible. So, what's next? How do we solve this cosmic cliffhanger? The answer is simple. We keep looking. Science never stands still, and the quest to answer this question is driving the development of a new generation of incredible instruments and experiments. On the astronomical front, new spectrographs are being built specifically for this purpose. Instruments like Espresso on the Very Large Telescope in Chile and the future arm of the Extremely Large Telescope are designed to be more stable and precise than ever before. This grand quest reminds us of what science is all about. It's about being curious. It's about asking big, bold, and sometimes uncomfortable questions about the world. Whether the constants are changing or not, the search itself is guaranteed to teach us something new about the universe. The universe's biggest mystery is still out there, waiting for us to solve it. And the journey to find that solution is one of the greatest adventures we can imagine. We are left looking out at the cosmos not with certainty, but with a deep and abiding sense of wonder.